Thermochemistry, 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 thermochemistry is the study of the energy changes that accompany chemical reactions. So, that usually, delta, capital delta, means a change in something. So this would be enthalpy change, and that can be, enthalpy is H, enthalpy change is delta H, and it's the heat added to a system at constant pressure. Enthalpy cannot be measured, but enthalpy change can be measured by getting enthalpy of the product and minusing the enthalpy of the reactants. In exothermic reactions, general profile, you have the energy, we'll do capital E, and you have the progress. The reactants have more energy than the products. It goes down because heat is released, and heat is energy, so it's an exothermic change. And the opposite is the case for endothermic reactants, products. Enthalpy change is positive, enthalpy change is negative. Exothermic, endothermic. Because heat is absorbed, which is why it's a cold thing. Heat is removed from the atmosphere, uses energy for the reaction. Now, as you know, energy cannot be created or destroyed, so it only changes from one form to another, which is why exothermic reactions, the amount of energy that leaves the system is the same as the energy gained by the surroundings. And for endothermic, I suppose, the amount of energy taken in by the system is the same as the amount of energy that is removed from the surroundings. So you just observe the temperature change. So, yeah. Standard enthalpy change is measured when fixed conditions are used, and the fixed conditions, the temperature has to be 25 degrees Celsius, which is 298, ooh, that's not 2, 298 Kelvin. The pressure is 1 atmosphere. The solutions have to have a concentration of 1 mole per decimeter cubed, and the substances have to be in their standard state in these conditions. So like water, because it's 25 degrees Celsius, it would be liquid. Sodium would be solid at this temperature and atmosphere, temperature and pressure. Yeah. Woo. For carbon, graphite is more stable than diamond. So, enthalpy equations, carbon you do C, and then you write graphite underneath it. So it should be used instead of C, S. And the symbol for the standard state of enthalpy change is delta H with a little symbol there. I'm not sure what Greek letter that is, but up close it looks like that. Yeah, that just means it's in standard conditions, that little thing does. The standard molar enthalpy change of combustion would be shown with the C there. For combustion, that is standard conditions and change enthalpy. This is a formation, and this is a reaction. Now the difference between these, standard enthalpy change of combustion is the enthalpy change when 1 mole of a substance completely burns in oxygen under standard conditions. So oxygen would be in, well, I suppose, yeah, in excess. Well, you just have enough oxygen to fully combust it, which means the only products are carbon dioxide and water rather than any carbon monoxide being formed. So an example being used here is CH4 which is methane, reacting burning in oxygen, form carbon dioxide and water, and because it's a negative enthalpy change, it means that it is an exothermic reaction. The standard enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions. So, like carbon dioxide being formed from carbon and oxygen. It's 1 mole being formed, and yeah, under standard conditions. And the standard enthalpy change of reaction is the enthalpy change in the reaction between the number of moles of reactants shown in the equation for the reaction. So, like, burning ethene and oxygen can be written as this. Yeah. So, rather than 1 mole of the substance being used or formed, it's just multiple moles. Yeah. Coincidentally, every single one of these are exothermic reactions, but, you know. Yeah. And you have to remember Hess's law as well, which is the total enthalpy change for a reaction is independent of the route taken from the reactants to the products, provided the initial and final conditions are the same. This is because, you know, conservation of energy laws, energy can't be created or changed, so if you get the same products from, if you know, the initial and final conditions are the same change has been made, whether you do it in one route or another. So, therefore, the total enthalpy change for a reaction is independent of the route taken from the reactants to the products, provided the initial and final conditions are the same. Yeah. So there's direct routes and indirect routes. We can also do an equation for that. So enthalpy change in 1 is equal to enthalpy change in 2 and enthalpy change 3. And you can use these to do expressions for systems. So, as an example, this one, I'll draw it out. A, B, C. This is enthalpy change 1, this is enthalpy change 2, and this is enthalpy change 3. So, if you work this out, it basically equals this equation. So if you go from A to C to B, then you add these together because they're going in the same direction, and then because this is in the opposite direction, you take that away. And if you were then to move that over to make it a positive, you move it, add brackets, move it to the other side, the negative becomes a positive, and therefore you get the equation here. And that's how you work it out. So another example you can have, so you have A, B, D plus E, and B plus C there. It's a little bit more complicated. Of enthalpy change 1, enthalpy change 2, enthalpy change 3, and this time you also included enthalpy change 4. So to work this one out, these are going in the same direction, so you do that, add that, minus that. It's because these go in the same direction. They're not working against each other, working together, so you add them, and then this is the opposite direction, so you remove it, and that means you can move that over to the other side, become a positive, and put an equal sign. So then it's delta H1 equals delta H2, add delta H3, add delta H4. And this principle can be applied to multiple equations. Yeah. There are ones where it's a little bit weird, where you have negatives. For example, if we have, say, A, B, C, delta H1 here, delta H2 here, and you have delta H3 here. As a matter of fact, you would have delta H1 plus delta H3 minus delta H2. Ooh. And if you move that over to the other side, it would become negative delta H1 equals delta H3 minus delta H2. But because you want this to be a positive, if you flip the signs on all of them, then the negative becomes a positive, the positive becomes a negative, and the negative over the positive again. I'm going to do the negative turning positive there, and minus delta H3. And that's the one for that one. Yay! So yeah, those was just some examples for you. You can also use, you can also calculate the enthalpy change of a reaction by using the enthalpy change of formation values. So if you have the enthalpy change of formation of nitrogen monoxide is this, and the enthalpy change of formation of nitrogen dioxide is this. kJ mol 1. You can get the from the question. You can get your balance equation. Oh, that's running off the page. Where is it going? And then with this information you can construct a cycle. So the overall enthalpy change, just enthalpy change 1, would be, you just basically extend the arrow there and do that, and you put delta H1 there. And because you know that the enthalpy change of formation of the nitrogen monoxide is that much, you can get nitrogen and then you can do that. So you have one of those, and oxygen. I'll just put the number 33.2 kilojoules per mole. Oh, that's running off the screen. The reason you know it is this at the bottom is because it's formation, which, as I previously stated, the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions. And 2 of half nitrogen would form 1 nitrogen. Same with this, and, you know, 2 oxygen. Ta-da! And then you can just apply Hess's law to that. And once you do that, you get minus 57.1 kilojoules per mole. You could also use the equation enthalpy change of reactants. One moment. Enthalpy change of reaction, not reactants, equals the overall enthalpy change of formation. This just means like the sum of. That just means the sum of. Minus the sum of the enthalpy change of formation under standard conditions, all of these are. Yeah, that can also be used. Although that is for formation values. If you have other values, like combustion, if you have combustion values, then it would be delta C. Enthalpy change of combustion under standard states. Oh wait, I've written this down wrong. So the enthalpy change equals the sum of the enthalpy change of combustion of the reactants minus the enthalpy change of combustion under standard states of the product. Oh, same for this, I believe. It is reactants minus product. That is the most important part of. Oh, the product minus reactants, actually. So products minus reactants. That is the most important part of it, whether it's products minus reactants or reactants minus products, at least when I was doing things, because it made things a whole lot easier if you knew what you were taking away. And in the case of in enthalpy change of reaction, it is the same as this. It's just instead of, you just write it differently. It is still reactant. Oh, it's the same as this one. It's the same as formation, but you just write it down with the reactants there, like with, as in the R there to symbolize that is the enthalpy change of reaction under standard conditions, but it is still products minus reactants. So basically, the most important thing you need to remember is that for formation, it is products minus reactants. I'll go on there. For combustion, it is reactants minus products, and for reaction, it is products minus reactants. That is what will help you with a lot of the equations. Yeah. Now, you can also calculate the bond enthalpies of things. Oh, no, you use the bond enthalpy values to figure out the enthalpy change. They'll just give you how much the bonds, how much energy the bonds require to be formed, and then you can use that to figure out the enthalpy change overall. So, there's an example here where they give you the bond value of 2 chlorine to chlorine bond, the average bond enthalpy, which was in kilojoules per mole, was 242. Double bond oxygen to oxygen was 498, and the equation was how would I write that? I'm just going to do the displayed formula which they've given us. So ClOCl, there's 2 of those, and it goes to 2 Cl to Cl bonds, and 1 of those. And you know that the enthalpy change overall is 160 kilojoules per mole. And what they're asking us to figure out is the average bond enthalpy of the Cl to O bonds in 3 significant figures. So, basically, we know this is reactants minus products. Actually, products minus reactants, not reactants minus products. I don't know why, but in my notes it says reactants minus products, when it's not even a combustion reaction. So we'll ignore that. It is products minus reactants, because, well, in the equation it seems to be a reaction thing. It should surely be calculating the bond enthalpy of reaction, because it's not being combusted, and there's not 1 mole of things being made. So, products minus reactants. So, because you know the bond enthalpy values of these bonds, you can figure out the bond enthalpy values of the products. Therefore, because you have 2 C to Cl bonds, it would be 242 multiplied by 2, so that would be 484, and because you have just one set of oxygen to oxygen double bonds, it would just be 498. So you'd add those together because those are the products, and you'd have to take away the reactants, which would be, you don't know yet, but you know, just take away the reactants, and that would equal 160, well, minus 160, as you know the enthalpy change. So then, you can rearrange this equation. If you figure out 484, add 498, which is 982, so it's 982, take away reactants, equals minus 160, so then you can add this to this side, because if you move it over to this side the negative becomes a positive, so it adds, so that would become 1142, and this would move over and the negative would become positive, and then you get the bond enthalpy of these, and because you know the bond enthalpies of 1, 2, so it'd be 1, 2 chlorine to oxygen bonds, but because there's a 2 there, it means there's 4 of them, so you have to do 142 divided by 4, which is 285.5. So then that would be, the answer to the question, that would be the bond enthalpy value of that, 285.5. You can't directly measure the enthalpy of a system, but you can find out how much heat has been transferred to the surrounding, and then use the formula to calculate the enthalpy change. So a calorimeter will be used to record the temperature change, which is caused by enthalpy change of the reaction. And a calorimeter is an insulated vessel which is used to determine any heat changes that take place in aqueous solutions. Usually, if you're in somewhere like school, you'd just use a polystyrene cup. That's the easiest thing to do. I have a diagram here. Polystyrene cup, and you need to make sure it's nice and insulated so that there's no heat loss. Now, you need to remember this formula: Q equals mcat, which is used to calculate the amount of heat transferred to the surroundings. So Q is the amount of heat transferred. The M is the mass of solution. In grams, usually of water. And because water has a density of 1 gram per centimeters cubed, the volume in centimeters cubed equates to the mass in grams. So if they tell you, oh, there's 50 centimeters cubed of water, then you can just put it down as 50 in the mass, because it's usually grams and it's the equivalent anyway. The C in MCAT is the specific heat capacity, usually of water yet again. And it's the energy needed to raise 1 gram of water by 1 degrees Kelvin, and that value is 4.18. That was a J. J, G, minus 1, K minus 1. Yeah, although some questions may give you a specific one they want you to use. And then this is just the temperature change, because it's just delta T. Delta stands for change in, T is temperature, so it's just the temperature change. Q equals mcat. It looks like it says cat, but that is a delta symbol. So Q equals MC capital delta to capital T, if you want to be specific about it. So because of temperature loss, if you have a graph and you want to get an accurate value of the temperature change, what you have to do is you have to extrapolate the curve back to the point of mixing, where you just do a line there, and then you can read it off of the side. You have another example here. It's terribly printed, but you can see better on the camera than you can in real life. And I have done a poor job there, but that's what the teacher gave an example of. And then you can get the value from here. Yeah, then you can use that for your equation. To calculate the enthalpy change per mole, you'd use this. So enthalpy change equals minus heat transferred from the surroundings over moles. With these questions, they usually, if there's long-winded ones, it's usually the same sort of series of equations you do. So, give you an example. Let's do calculating the enthalpy change of combustion. So, the combustion of 0.75 grams of ethanol raised the temperature of 250 centimeters. This is the worst camera I've ever seen in my life. Centimeters cubed of water by 19.5 degrees Celsius. Calculate the enthalpy change of combustion of ethanol, which is C2H5OH. I'm going to try and maybe reduce like that. Is that easier to see? Or I think that's a little bit easier to read. Oh, unless it's 1 second. I think it's just my computer screen, actually. I think my computer screen might just be a little bit bad. Anyways. Yeah. So, calculate the enthalpy change of combustion of ethanol C2H5OH. Step 1, you'd have to use Q equals MCAT to calculate the amount of heat transferred in the experiment. So, in this case, you know the mass is 250 grams, because that's the same as 250 centimeter cubed of water. You get the, I don't remember what that is. See, even I need to remember this. It's important to remember what these individual things mean. To get the specific heat capacity, I believe they've given it to you. Oh no, it's always 4.18. And then to get the change in temperature, you just, well, yeah, get it from the question. So it's 19.5, and then you use that to calculate the amount of heat energy transferred. So now that you know the amount of heat energy transferred, you can calculate the moles of the reactants, where it's just, you just get the MR and divide it by, you don't get the MR and divide it by anything. I'm being silly. You get the mass and divide it by the MR, because moles equals mass over MR. So now that you have the moles of ethanol, and you have the change in, and you have the amount of heat transferred, you can use the equation enthalpy change equals minus Q over N, because you have Q and N now. So then you use that, you do minus of this number you got here. Don't forget to do the minus of it, because sometimes I do that and you get the wrong answer completely. Do the moles, and then you can get it in joules per mole, but usually they ask it for kilojoules per mole, so you just divide it by 1,000, and then that's it. It seems relatively simple, but you need to actually remember the steps and be able to apply that to different types of questions. And finally, you also need to know about bomb calorimeters. They're used to obtain more accurate measurements of energy changes when fuel burns. So the reactions are placed inside the bomb, and then there's a supply of oxygen going to it. The electrical heating device starts the reaction, and there's a stirrer that ensures there's a uniform temperature. The water absorbs the heat of the reaction, and then the thermometer records the temperature rise of the water, and that's basically how they work. And that is all of it. If I were to recommend that you do anything for this topic, just practice reading your graphs, practice doing your equations, and try and memorize the formulas they give you, because, I mean, if you don't know the formulas, you can't do the equations. If you just practice doing the equations and do past paper questions, then that is going to help you memorize the equations themselves. So yeah. well, that's thermochemistry. Bye.